Okay, so here's these last two questions. So question 6, in this diagram here, resistors R1 and R2 have resistances of 40 ohms and 20 ohms respectively. So again, first thing I would do would be mark those on. So R1 is this wee one here, so it's 40, and R2 is this one, so it is 20. Part A is to calculate the voltage you would expect to observe on the voltmeter. So that's looking for this voltage here. One way we actually could do it, which I haven't done, is just to use the ratio of the resistances. So we're going to have the 12 volts splitting up in the ratio of the resistances. So this one here is double the resistance of this one, which means that we've got two numbers that need to add to 12, one of which is double the other. So this one's actually going to get 8 volts and this one's going to get 4 volts. But let me show you how to actually do that properly, because that is quite a sneaky wee trick, that one, that works. So to get the voltage across here, we're going to end up using V equals IR. We've got the resistance, we need the current. And that, because this is a series circuit, it's going to be the current that's leaving the power supply. So that's the first bit in my working out here. The current leaving the power supply is going to be I equals V over R, just rearranged V equals IR. V is the voltage of the power supply, and then the resistance, remember, that we use is the total resistance of the circuit. So it's these two added in series, so 40 plus 20 is 60. So that tells us that we've got 0.2 amps flowing through, flowing around this circuit. Which means then, to get this voltage here, I can just plug that into V equals IR. So V equals IR, current is 0.2, resistance here is 40, and that gets me 8 volts. And then B, what assumption have you made about the resistance of the voltmeter itself? Well, I'm assuming, I've forgotten where I was again, so it was Mr. Ross this time, not Mr. Reid. What was I doing? B, what assumption have you made about the resistance of the voltmeter itself? Yeah, so we are going to be assuming, remember we always say, like, we act as if it's not there in the circuit. So we're assuming that the resistance of this is really, really high, that no current from the circuit goes down here, because then this is just a wee series circuit with the current the same everywhere. So the resistance is very high, so that no current goes down there. Terribly worded, probably. Right, and then number 7, let me just rearrange my pages here. Right, okay, so number 7, look at the circuit here, copy and complete the table which is on the top of the next page to show the effective resistance between X and Y, so between these 2 points here, of the 4 different switch settings. So all my working out is here. So with both A and B open, so for this first one here, if this switch is open and this switch is open, then it's as if there's no current flowing in any of these. So we have just a 6 ohm and a 3 ohm in series with each other. So our total resistance there is just going to be 9 ohms. B is with A open and B closed. So with A open, then this one isn't there. Let me hide that. B closed means that this one is there. So now we've got a 6 and 4 in parallel with each other, which is then in series with the 3. So this is my working out for that. So the 6 and 4 in parallel with each other, they combine to give us the 2.4. And then that 2.4 is in series with the 3, so I've added it on, and I've got 5.4 ohms for that one. So that's my wee 5.4 in there. C then is with A closed and B open. So now if B's open, no current can flow through there. So now we've got 12 and 6 in parallel with each other, which is then in series with the 3. So this is my working out for that. Getting the parallel combination of the 12 and 6 first of all gives me 4. And then adding that onto the 3 in series gives me 7 ohms for that one. So that's here. And then for part D, I labelled these A, B, C and D. Both of them closed means that all 3 of these are there, because if these are both closed, then current can flow through all 3 of these branches. So if you've got 3 in parallel, then you can't use that wee multiply over add rule. You need to go to the 1 over rule. So 1 over RT is 1 over 12 plus 1 over 6 plus 1 over 4. That gives me 1 over RT is 1 over 2. Turn it all upside down. Total resistance of the wee parallel bit is 2. Add it onto the 3 in series and we get 5. So there we go. Then number 8. This is quite annoying because I'm going to end up flicking backwards and forwards. A student investigating the relationship between the resistance and the cross-sectional area of a resistance wire of length 1 meter obtains the following results. The material from which the wire is made is always the same. So basically they're saying it's a fair test. The only thing they're changing is the cross-sectional area. So part A is to fill in the table. So because I hadn't left myself no room for my working out, I did this all over the page. Now, I want to show you, before I show you my working out. Right, so the ones in yellow were the ones that you had to fill in. Everything else was already filled in. You can actually use the wee, you can do this without doing all the working out I'm about to show you. So do you remember the rule, as the cross-sectional area increases, the resistance decreases, so the two things are inversely proportional to each other. That means if you double the area, the resistance is going to fall by half. If you triple the area, the resistance will fall like to a third. So here, area going from 0.5 to 0.1, so it's doubled. We know the resistance is going to half, basically, so 12. Same we can do again, I'll do the 4, so from 2 to 4, area has doubled, resistance will half from 6 to 3. This one here, I would probably go from here to here, so 1 to 3 has been tripled, so it's going to, you divide by 3 then, so 12 divided by 3 gives you 4. But this working out that I'm going to show you then comes in handy later on in the question. So to do the proper working out for that then, so take one of the values that you already know. So they actually give you 2. You could have done either of these. I used this one. So I said, right, resistance is inversely proportional to area. I can rewrite this as R equals K over A, so some constant that links these two things. Substitute in my 24 for resistance from here, which had a corresponding area of 0.5, so it goes in there, and then that gets me K to be 12. So now that I know that the constant for this particular situation is 12, I can just replace that with the numbers I know. So to get this one, R equals K over A, K we know is 12, the area was 1, so that gives me my resistance of 12. Same here, R equals K over A, K is 12, this time our area was 3, so our resistance is 4. And then the exact same working out there to get that 3. Okay, so you could just do it that first way, but you'll see in this next part I do go back to use that wee constant. Right, part B is this a sneaky wee one now. Calculate the resistance of 50 centimeters of a wire. Well, oh jeepers. Whenever I saw that, I automatically scanned back to the original question and was like, look, all these figures in this table are about a wire which was a length 1 meter, so be careful with that, right? A cross-sectional area 1.5, which is awkward, right? Made from the same material. So here's what I did. Length is 50 centimeters, area is 1.5. I just listed the information. Stop me flicking backwards and forwards. Here's my wee note. So this is half of the original length. So if we calculate the resistance of 1 meter with a cross-sectional area, with this cross-sectional area with a cross-sectional area of 1.5, then once we get that, you can just divide by 2 to get the resistance for 50, because remember, resistance is directly proportional to length. So my working out for the 1 meter is using my information from part A, so R equals K over A. R is, remember we figured out K was 12, over the area, which they're asking about is 1.5, so that got me a resistance of 8 ohms. But that was for the length of 1 meter. So for the 50 centimeters, we just divide that by 2. So R is 4 ohms for that one. Okay, that is it. Some of those are really tricky. So next lesson we're going to be doing some past paper questions to give you a wee bit of a better idea of the type of questions that get asked in exams. Okay, see you soon. Bye.